So now the value of flow. So what is the value of the flow? So value of the flow is the total flow that happens from the source to the terminus or the sink. This means that like if you are say transporting things from S to T, what amount, like how many tons of material or something can be transported from S to T. That is what we want to find out. And so how do you get that? Like, so whatever goes out of S, right, is basically what is supposed to reach at T, because we say that we define a flow to be those assignments that what we can send, such that whatever comes into a vertex, internal vertex, is also going out. So except for S and T, if something goes out of S, it should always reach T. So therefore, if you find out what is all leaving S or what is all reaching T, they should be actually equal to the material that is transported. Right? So basically, that is the value. So the value of the flow given a network N and a flow F, the value of the flow is basically defined as summation over all the vertices in V, f of S comma V. Right. So S comma V is the arc, and whenever there is an outgoing arc from S, you look at the flow going out of it, and that is f of SV, and you take all this thing, and then you see if there could be some incoming arcs also, right? Sometimes, and then you subtract, right? So summation overall V in V, f of V comma S, right? So basically all the incoming flow must be subtracted, and this is basically the value of the flow. So in the example given above, you are saying that like from S, the flow takes 11 out and then 8 also out. So 11 plus 8, which is 19. And therefore, if you look at T, you should also see that, what comes into T must also be 19, because if it is a flow, this should be the case. So, and here you can see 15 plus 4 is again 19. So, yeah. So that is what the value of the flow is. Now, one of the natural questions one can ask in the flow theory is how to maximize the flow, because you have these constraints like the capacities of the edges or the network capacities are basically the constraints that we have, like maximum that we can transport, and with all these constraints we want to maximize what we can actually send, right? How much data can be transferred or how much material can be transported. And this asks the natural question, what is the maximum flow that is possible, right? Given the constraint that, like, for every internal vertex, the incoming flow must be equal to the outgoing. So that is the question called maximum flow problem. And a flow is maximum if for any other flow, right, f dash, the value of the flow is greater than or equal to the value of the other flow, right? So if f and f dash are flows, f is a maximum flow if for every flow f dash, right, that we can define over n, the value of the flow f must be at least as big as the value of the flow f dash. Okay, so some questions for you. So given a network n and let's say some real number alpha in 0, 1, show that if f1 and f2 are flows, then alpha f1 plus 1 minus alpha into f2 is also a flow, right? And where we define alpha times fi of uv, right, for the arc uv is alpha times fi of uv. So yeah, so I should I think alpha fi, yeah. alpha Fi of uv is alpha times Fi of uv. Then let n be a network with multiple sources and multiple sinks. Okay. So suppose so when we defined network flows, we defined we have a starting vertex called S, then you have a terminal vertex called T, right? And then we have all these arcs, which is basically a digraph. And then we defined our question on this. But now it could be possible that a factory or a company has several factory outlets and it has several destinations where it wants to send the material, right? So in that case, you could have several sources and several terminals or sinks. Now, how do you represent such a question, right? So can you represent such a question in our network flow theory? Well, one can, if you think about it for a few minutes, you will be able to see that one can convert that question to a single source, single terminus flow question very easily. So that is what I want you to do. So given a network N with multiple sources and multiple sinks, as let's say given below here, right? Convert into a single source, single sink problem. Okay. So here is the network that is given to you, right, with the capacity constraints. Now take this and then produce another network question. But what we want to maintain is that if you maximize the flows, right, in either of these networks, we want to get the same answer, right? So any maximum flow in the first network, right, should translate to a maximum flow in this network also, and any maximum flow here must have a corresponding. I mean, like we may not get exactly the same flow. It doesn't matter, but the flow may be different, but the maximum value of the flow will be the same. That's what I wanted to say. So the value of the flow must be maintained, and with respect to that constraint, how do you convert this to a question of a single source, single terminus question? Okay, so think about that. Then a network, let's say n is given with let's say vertex capacities as well as edge capacity. So now instead of so far what we have seen is that we have a flow network where the edge capacity is that. But now we can say that okay, for each node, right, each vertex, the maximum data that can be transferred through this node or is also upper bounded by something, right? So there could also be like vertex capacity, right? So you don't allow too many too much traffic into the intersection, maybe, right? That kind of some constraints may be there, like in a city. So if the traffic passes through city, then there may be there will be some constraints saying that okay, if there is more than this many traffic, then of course we will not allow. We will just ask them to sit somewhere else, right? or reroute it. So therefore, we have basically vertex capacity is also possible. Now, given such a question, can you convert into the thing we already know, right? Like the question with just edge capacity. So how do you convert a question with vertex and edge capacity to an equivalent question with just edge capacities, right? Such that again, such that the maximum flow in the network n dash has the same value as the maximum flow in the network n, right? So we want to create a new flow network, right? Of course, the capacities of the edges may be different now, but the maximum flow value will still be the same. So how do you do that? Is it possible? Okay. Okay, so I was actually hoping to give some more reading assignments to the remaining students who has not yet got it. But now I find that some of the students are not even present in the classes anymore. I don't know whether they are actually in the course. It's not yet clear. So well, let me anyway list the questions, and then whoever is remaining in the course can choose what they want to present. Okay, so here are the questions for the reading assignment. Let's say you have the maximum flow problem, and then like we just stated before, right? Just a few minutes before. Now, I want you to look at the maximum flow algorithms. For example, the classic algorithm of Ford and Fulkerson, right? And one can basically ask to look at these questions like so how does this Ford Fulkerson algorithm work, right? So it basically starts with a zero flow, right? So we already said that zero flow is a valid flow because you can just assign zero to every edge. It will of course honor the capacity constraints, and then the sum will be the same for internal vertices, and so it's a valid flow, right? So you start with a zero flow, and then you can define from the given network, we can define what is called a residual network. Okay? So it's basically another directed graph with with additional R's or like less R's depending on the case maybe, and then with some capacities also, like which comes from the current state, right? So the current network capacities plus its current flow will define the the residual network, and then its flows. So this one can define. It's not difficult. It's a nice reading. So look at the residual network, then look at the basically define it, and with a couple of examples, and and prove some lemmas. And then after this they will look at what is called augmenting paths. So we will see what are augmenting paths, and then again give some examples for the augmenting paths, and then a couple of results on that. Then plus one can define what is called cuts, right? So we already know what is an edge cut, so we can now define cuts in networks also, right? And then there will be some associated results, and then one can show that the maximum flow in a network is going to be determined by the so look at the different possible edge cuts of the network, and then find the one which attains the minimum capacity of the cut, right? And now if there is a cut of the edges which does not allow more than this much to be transported between S and T, right? So there is an ST cut which basically says that if you remove these edges, of course there is no connection from S to T, right? And therefore, if the minimum capacity, the capacity of this cut is bounded by some number, we cannot have, we cannot hope to have a flow value larger than this, because any flow must basically go through these R's at some point, right? So this is going to be an upper bound for the maximum flow, and one can actually show that this maximum flow is attained. And therefore it's called max flow min cut theorem. So the maximum flow is actually equal to the minimum cut capacity. And one can prove this. It's very easy to prove if you assume the edge weights are rational numbers. But even otherwise, one can show this to be true, right? So yeah, so this is what I want some of you to read and present. And one of the best reference book I can suggest is Introduction to Algorithms by Corman, Lizards and Rivest, and the third edition of this. So this basically the lemma numbers that I have given according to this. So this is a nice question, and one can also try to present the algorithm of Ford and Fulkerson with some example of how this is executed. Now, who all can take this? Well, now who are all remaining? We need to figure out, and maybe one can do what one can do is to so you basically, anyway, all of you has to read it, right? So whoever is remaining, please send me a message saying that, you would like to present from these topics or not. Of course, I will have something other than this also. Here is another question. I thought that maybe this is a question that maybe Nishan can present. Basically, an application of Euler in trails to algebra. So this nice example is given in the book by Bolabash called Modern Graph Theory. And if you look at the section 1.5, this is a nice problem. So maybe, I suggest Nishank try to present this, and all of you can of course read it. Is it okay with you, Nishank? Okay. Okay, so coming back to this, so this was my plan. Now I don't know how many students are left to do this, so maybe you can take two, two students can take two each or something, two parts of this. It's not very long. It's simple. Okay, so once we finish with that, I think we will not spend too much time on flow anymore. And essentially, what we want to look at was this Maxwell Cut theorem and the algorithm associated with it. Of course, one can expand this. There is another entire subject called flow theory is there, but we are not going into that at the moment. Yeah, so we now go to another topic called matching theory. So you are already familiar with what's called independent sets, right? So what are independent sets in a graph? Independent set is a set of subset of vertices. Yeah, so independent, so an independent set in a graph is basically a subset of vertices where no two of them are joined by an edge, right? So basically, these vertices as a subgraph, there is no edges between them. Now, if you look at a collection of edges, right, where each edge, so no two edges share a vertex. So such a collection of subset of edges is called a matching. So example, it's like maybe this one. Then of course I cannot select any of these three edges or four three edges incident to this. Maybe this, I can select this, right? Then I can select maybe this one, this one, right? So this is basically a subset where no two edges have vertex in common, and this is called a matching, right? And another matching we can define this one, right? Choose this one, maybe this one, right? And even this one. So this is another matching. In fact, a single edge is also a matching, right, by itself. So you collect a subset of edges where not all of them share a vertex. So that's called a matching. So a matching is basically a subset of edges which is pairwise disjoint. Suppose you have a matching, right? Let's say M is a matching in a graph G, right? Then the vertices which are incident to the edges are called, said to be saturated by the matching. So in this example, right, according to the blue matching, right, these vertices are all saturated. These vertices are saturated. but the remaining two vertices are not saturated. So this one is not saturated by the blue matching, I mean, right? This one and this one. But on the other hand, the yellow matching saturates all the vertices of this graph, right? So if you look at the, I don't know, is it yellow or green? I am a little colorblind. I cannot really distinguish between these. So, so this other matching that we presented basically saturates all the vertices. And if a matching saturates all the vertices, it is said to be a perfect matching. So, so you have this concept of being saturated, and only matchings which saturates all the vertices is called perfect matching. It's also called one factor. Now, this perfect matching, of course, will not be there if the number of vertices is odd, right? In a graph, if the graph has odd number of vertices, you can never have a perfect match. But it is not necessary that if the number of vertices is even, you will be sure to have a perfect match, right? Because one can have something like this, right? There is even number of vertices, but there is only one edge that you can choose, right? It saturates only these two vertices, and the other vertices will remain unsaturated. So therefore, one interesting question is that is there a perfect matching for a graph? We will not consider that question in this course, but it is a very important question. So again, this graph has a perfect matching. For example, if I choose this, and this, right? This forms a perfect matching, which saturates all the vertices. On the other hand, this graph has odd number of vertices, therefore it has no perfect matching. If you choose any of this, you will have at least one vertex which is not saturated. Now, we will come to see why matchings are important soon. So here are some couple of homework questions, like find or count the number of perfect matchings in the complete bipartite graph KNN, and also find the number of perfect matchings in the complete graph Kn. Right. The second question will be slightly more difficult than the first question. Now, again, once you have a matching, you can ask like what is the largest size of matching that is possible. Now, suppose you start with a graph and you have a matching and you are not able to add any more edges to make any larger matching, right? In such a case, it is called maximal matching. So, for example, suppose you have this graph, right? And now you start by picking some edges to add into your matching. So I pick this edge. Now this edge, is added to the matching, right? So I have the matching M, and I'm adding this to the matching, right? Now, of course, I cannot pick this edge or this edge. So now I can pick, either this or any of these two edges. So let me pick this, right? So I pick this. Now I see that in this graph, I cannot pick any more edges, right? And add it to the matching M, right? Because now, I cannot extend it anymore, right? I cannot pick any edge which is not in the matching and add it to it. So this is a maximal matching. So a matching is maximal if you cannot add any more edges outside the matching to this M, so that you get another matching, right? So if you cannot keep the matching property by adding any edge outside the matching, then it's a maximal matching. So in this example, M is a maximal matching. But then the maximum matching is is a matching of the largest cardinality. Right? So if you are looking at the maximum matching in this graph, this is not a maximum matching. It's a maximal matching, but it is not maximum. Why that? For example, I can, instead of picking this, I could have picked, for example, this and this. Right? then I will get a matching M dash, right? And this M dash has 3 edges, right? It has more edges. And one can actually show that you cannot have more, because of course all the vertices are saturated. So therefore we cannot pick anything more in this example. Right? So, but maximum matching need not always saturate all the vertices, right? For example, this graph, we saw that there are, only 3 is possible because there is odd number of vertices, and therefore one vertex is not saturated. And since we have all the other vertices saturated, it is also a maximum matching. But again, that is not necessarily the case, right? If you have things like star, right, you have several possible, right? Several possible vertices which are not saturated, but of course the maximum matching is maximal as well as maximum, right?
Perfect matching is always a maximal matching, right?
Yes, perfect matching is maximal because all the vertices are saturated. We cannot do anything, right? It's a maximum as well as maximal.
Yes.
Okay, so what we are saying is that a matching M is maximal if there is no edge in G minus M, such that M union E is also a matching. Right? And a maximum matching is a matching of largest size, and this size is denoted by nu of G. Of course, different books follow different notations. I think in Douglas West's book, they follow a different notation. But I would like to use nu in this case. So maximum matching is a matching of larger size denoted by nu of G. So nu of G is the cardinality of the maximum matching. Okay, I think I presented this example already. Yeah, so 2, 3, and 4, 5. Right, this one is a maximal matching. On the other hand, 1, 2, 3, 4, and 5, 6 is a maximum matching. Now, suppose you are given, a matching M in a graph, right? And suppose I look at the vertices and the other edges, and I define a path. This path alternates between the edges of M and the edges not in M. Let's say. So let me look at this. Right. I have this this graph, and I have this matching, right. So this is our matching edges. Let's say M1. Right. Start with M1. Now I define a path which, let's say, it can start in any of these vertices, right? And it alternates between the edges which are in M and not in M. For example, I can start from here, right? This is an edge not in M. Then I select an edge which is in M. Then I select an edge not in M. Then I select something in M, etc. Right? Now this such a path is called an M alternating path, right? Because it basically alternates between the edges of M and edges not in M. So an M alternating path is basically a path which alternately uses the edges in M and edges not in M. Now, suppose for some M alternating path we are looking at, right? The endpoints of this path are both unsaturated by M. Then we say this is an M augmenting path. So the example that we looked at is not an augmenting path; it is just an M alternating path. But on the other hand, I could just look at this path, right? Starting from here, this, and this, right? The entire path, right? In this case, this entire path starts from a vertex which is not saturated by M, then ends in another vertex not saturated by M. So this is called an M augmenting path. Right? It's an alternating path which starts and ends in unsaturated vertices. Now, if you look at it carefully, you will see that the moment you have an M augmenting path, you will be able to find a matching of larger size in the graph. Right? So given this matching M, you can slightly modify M, right? You are not keeping exactly M as it is, but you are going to modify M, and you are going to get another matching of larger size. Now, how do you do this? Maybe it's a good idea to think about this. So, given an example like this, how do you come up with a a matching of larger size by looking at the M augmenting path? Now, because the path is M alternating and both endpoints are unsaturated, you see that there are the vertices at the endpoints of endpoints of this path are not saturated. So there is more unsaturated, not unsaturated, more edges which are not belonging to this matching than the edges that are actually belonging to the matching. Right? Because you start with an edge which is not in the matching, you end with an edge which is not in the matching, and you alternate between them. So therefore, the number of edges in this M augmenting path which does not belong to the matching are more than the number of edges which belong to them. In fact, it's exactly one more, right? So if you have an augmenting path, what you can do is to just switch, right? So you say that, okay, I'm going to add these guys to the matching and remove these guys from the matching, right? Okay. And since these guys were saturated, or they are still saturated, right? And I get one additional edge in the thing, and it saturates more vertices. So therefore, I get a more edges into the matching. Now this I can do even if I don't put all the edges of the matching into this M augmenting path. In fact, for any subset also one can do this. So this is something that you can observe, right, if you look at some examples. And here is another example. So here several alternating paths are given. Right? For example, P1 is an M alternating path starting from this vertex, and then it goes to goes to this vertex, right? Then of course our matching is the blue edges, right? Okay, so all the blue edges form the matching edges, and then from P1 I can go here, then I go to this, right? So I take this, and then of course I'm looking at this yellow or green, whatever edges, right? And I end up in this part, right? This is an M alternating path, and since these vertices, right, this vertex and this vertex are not saturated by M, this is also an M augmenting path. Now, so now what about P2? Right, P2 is an M alternating path, right, which starts from this vertex, let's say, and you take the blue edge, right, then the white edge, then the blue edge, then the white edge, then the blue edge, the white edge, and then the blue edge, right, and it ends here. And this is an M alternating path, but it is not an M augmenting path, right? Because the vertex, the starting vertex and ending vertex, neither of them are unsaturated. In fact, both should be unsaturated. Again, P3, one can see starting from this vertex, right, going here and ending here, right? So this is just two edges, and this is also not an M augmenting path because this vertex is not saturated, is saturated, and this one is not saturated. Okay, then P4 is starting from here, right, and just takes these three edges. But this is also an M augmenting path because these edges are, these vertices are unsaturated, right? The starting vertex and the ending. So we have two M augmenting paths we saw here, and then all of them are M alternating paths. Now, since it is M augmenting, we know that we can now find a larger matching. How do you do that? Well, what I am going to do is to just let's say, suppose I take P4, right? If I take P4, what I can do is that I will just remove this edge, I mean from the matching, right? And these two edges I will put into the matching, right? Then this one is not in the matching. So one can see that there is two more edges, right? I mean, there is one extra edge now, right? Instead of this one edge, you have two edges into the matching, and all the other matching edges are kept as it is, and we get a matching with one extra edge, right? So we increase the size of the matching. But instead of this, we could also taken, for example, the augmenting path P1, right? And we could just do the same thing here. It will not change the size by more than one again, right? One augmenting path will only change by one, right? So instead, I could have taken this and then picked up these edges for the matching, right? Instead of and then they will form and they remove the blue edges in the path, and you will end up in a another matching of exactly one additional edge. So this is how the augmenting path helps to increase the size of the matching, right? It turns out that a matching which is not maximum, right? Even though it is maximal, a matching which is not maximum will always have some augmenting paths. Uh, we want to see. So if G is a graph, M is a matching, and we have an augmenting path, let's say P, then if you replace M intersection edges of P, right? That's what we just did, right? We took the matching edges from P, right? Removed it from the matching, and then put the edges in E of P, right? The edges of the path minus M, right? All the matching edges are, other than the matching edges, you take the edges and that put that to here, then you will get a matching with exactly one extra edge, so that the M prime has strictly greater than M, right? Or cardinality of M plus one edges. So maximum matching, one can use it as an algorithm. Okay, so I'm not going to formally present the algorithm, but one can read about this if you want in the book that we have, the glass versus itself, I think. So you take with this start with any matching, right? Because it is if it is maximum, then there won't be any augmenting path. If it is not maximum, you will be able to find some augmenting paths, and then find the augmenting path. Do this replacement, get another matching, and see whether that has another augmenting path, and keep on doing this, and eventually you will end up in a matching which is maximum matching. So I think we already saw a few examples, right? So we have this matching blue edges, and then you have the augmenting path starting here and here. I can just replace the matching edges with these two, and then remove this. I get a larger match. Now, to help you prove that this augmenting paths will mean that you can make it larger, and you can always find an augmenting path. I will define something for you. So the symmetric difference of two graphs, let's say G and H, is basically the set of the subgraph formed by the edges, right, which appear in exactly one of these graphs. So if you have let's say this graph as G and this as H, right? So what I am going to do is to look at the edges in the symmetric difference G, symmetric difference H, is this edge 1, 2 is appearing here as well as here. So I cannot put that here. Right? So 1, 2, there is no edge. 1, 4, there is no edge here, but there is an edge here. So 1, 4 will appear here. 2, 4, there is no edge in the edge, but it is there in G. So I will have 2, 4 here. 2, 3 appears in G, but not in H. So therefore 2, 3 will be there. 3, 4 appears only in H. So therefore 3, 4 will be there. Right? And you have all possible edges of G or H appearing, right? Considered already. So therefore, we have the symmetric difference graph defined like this. Okay. So given two graphs G and H, the symmetric difference is the graph on the same vertex set whose edges appear in exactly one of G or H. Again, some other example, you have G as well as H, and the symmetric difference will be this graph, right? One can again check 1, 2, 1, 2 will not be here, right? Then 1, 5, 1, 5 is both present, so therefore it's missing here. 5, 4 is also missing here because of that. On the other hand, 3, 4 is appearing only in H, so therefore 3, 4 edge is here. 2, 3 appears only in G, therefore 2, 3 appears, no, 2, 3 appears in both, so it's not there. Then 1, 3 appears in only in H, and 1, 4 appears only in G, and that's it, right? So we have all the edges. So here is the theorem that we wanted to prove, that a matching M in a graph G is maximum matching if and only if G has no M augmenting paths. To prove this, I will give you a hint, right? So I will leave it as a homework. Give you a hint that first what you do is that you show the properties that you can think of, right, of the symmetric difference of any two matchings, and this symmetric difference you can find out that they have some special properties, some special structure, right? What kind of graphs can be the symmetric difference of two matchings? Take any two arbitrary matchings in a graph, and what is the symmetric difference of these two matchings? Okay, so study this, look at some examples, and find out what you can come up with this, right? The properties of this graph, right? The structure of this graph, and if you get that, then you can easily prove the theorem. Okay, so just use that property, you will be able to prove this theorem. The matching is
The vertex is the vertex has all its edges in both the graph. Then it's symmetric difference may this vertex will be the single vertex without any edges, right? Or will we not have the vertex?
yeah. So the vertex will be there. I mean, yeah. So it's on. So we have already defined it here clearly. The symmetric difference is on the vertex set V, right? So this says that the vertex set is the same. Okay, so now another result I want to look at. Okay, I think I don't have time to do that today. Yeah, so okay, let me anyway start with this. So we have the suppose we have a bipartite graph. Okay, so suppose we have a bipartite graph, and we are looking at matchings in the bipartite graph. So we have bipartite graphs when we're looking at matchings in the bipartite graphs. Now suppose we have a matching that saturates all the vertices of X. Okay, so the matching saturates all the vertices of X. Let's say. Okay, so you have right. You have some matching maybe which saturates all the vertices of, let's say, X. So okay, let me say this one, and this one, right? So if this matching, if I select, then all the vertices are saturated. Now, if this is true, right? So if a matching saturates all the vertices of X, then if you look at the neighbor set of any subset of X, right? So take any subset of X, right? Let's say this one. So I take the neighbor set of any subset of X. You can immediately see that this will have at least as many vertices as in S, right? So if you choose S as your subset, then if there is 3 vertices in S, then you will have at least 3 vertices in the neighborhood of S. Why is this? Because all the vertices in this bipartite graph, right? All the vertices of the subset S are saturated by matching edges. Now, if you look at just the neighbors of the matching edges, right? Whatever is the matching edges that we are choosing, they will all be, different vertices, right? Because each of the edges are matching edges are all disjoint, right? And therefore, uh, for each vertex, you have a corresponding vertex in the neighborhood of S. There could be more, right? So therefore, the cardinality of the neighborhood of S will be at least the cardinality of S for every subset of X, if X is saturated, right? By some matching. Now this is immediate, right? One can immediately see because there is a one-to-one correspondence between these guys, and if you pick any of them, you will have at least that many neighbors in the neighborhood of the entire vertex set, right, that we are looking at. So cardinality of the neighborhood of S is at least the cardinality of X for every subset of X. Now, on the other hand, it may not always be the case in any arbitrary bipartite graph. For example, if you look at this graph, right, you have let's say these three vertices. Let's say is S subset of X dash, right? What is the neighborhood of this? This is basically this vertex and this vertex together, right? This is the only thing, right? That is there. So the neighborhood of S is only two vertices, where S has three vertices. So this property is not true in this graph. I claim that if this property is not true, then there is no matching which saturates X prime, right? I mean, one can see why it should be the case. But what is even more surprising is that if for every subset of X, right, this property holds, that every subset of X, S is the neighborhood of S has at least as many elements as in S, then one can show that bipartite graph will always have a matching which saturates X. So this is the interesting part. This is what we want to prove, and we will. This is called the Hall's theorem. So we are going to prove this theorem of Hall in the next class.